All right, students. Let me see how many of you are able to join, right? Okay, so I still believe that you want to join, but due to some problems you are not able to join. So 15 students were able to join. I don't know what others are doing. All right. Okay, so we'll get started, students. So today's plan is we will talk about sorting. Basically, we are trying to talk about the sorting which is based on comparison. Okay, so that's why the question that we asked yesterday is uh, whether any, do we have a better bound, do we have a better upper bound, So it is all n log n, or, we
Excuse
have,
me.
pardon me.
I'm hearing a buzzing sound, like a constant sound. I think it's my laptop itself. Is anyone else also hearing?
It's fine for me. I don't find any disturbance.
Okay, okay, okay.
Maybe,
Nice.
maybe
My,
Priya, you can just log out and, I mean, not log out, leave and come back again, maybe sometimes.
yes, ma'am, yes, ma'am, yes,
Hmm? Yeah, yeah,
ma'am.
yeah. So, all right, students. So we were discussing yesterday, whether can we find a better bound? Can we do better, right? So you people said that, we have bucket sort or Reddick sort, then, it is not O n log n, it is less than O n log n. So here we are basically trying to talk about comparison based sorting, wherever we are trying to do the comparison. Okay, so let us see, and we will get the solution, whether it is possible or not in comparison based sorting. We are not assuming now, we are not including the counting sort or those kind of things now. Okay, so we are assuming the sorting which is comparison based. Okay, so what happens? Comparison based sorting is sorted order is determined based only on comparison between input elements. Okay, so we are not considering the other kind of sorting. Let's say count sorting, where you said yesterday that we are calculating the frequency. What we are assuming is for sorting, let's say sorting numbers or sorting the elements, we are always doing the comparison, right? So we do such kind of comparison: ai less than aj, greater than aj, ai is equal to aj, less than equal to or greater than equal to. Okay, so so do any of the sorting algorithms, we are assuming that, we do not have any additional information based on frequency, or we are not assuming that we have bucket sort kind of a thing. So we have been just given random numbers, and we are supposed to sort them based on the comparison, suppose. Okay, so we are talking about comparison based sorting. Okay, so so in the class of comparison based sorting, we know that, o n log n is the upper bound that we are going to get. That, it has to be less than or equal to o n log n. Okay, the complexity. Okay, so, and we have also seen, in, let's say, in Java and many other languages, for a class of objects, sometimes we need to sort them. Okay, we need to sort two objects, right? So what do we do in that case? We define our own comparator. We can have a function which we call as comparator, and basically what that comparator does, suppose you are supposed to sort two objects. Okay, maybe there are two student objects and you want to sort, so in which sense you want to sort them, that you will have to define, right? You want to sort these students based on their height, you want to sort these students based on their CGPA, you want to sort the student, many things, whichever thing you want to sort, you will have to write your own comparator. But everywhere you are going to do a comparison. So that comparator may be doing comparison between two, three things or between a particular thing, right? So that is what we are talking about, comparison based sorting. So any comparator we write, it actually compares any two elements. Okay, and wherever we are applying comparison based sorting, our comparator will be helpful. Okay, so the question is now the same question we are asking now, we are being specific, that yesterday you said yes, we can do better than o n log n if, in the class of sorting algorithm. Now our question is, can we do better than O and log n for comparison based sorting approaches? Okay, so we are being specific to comparison based sorting and approaches. Okay, so what exactly comparison based sorting approaches do, right? So what exactly we do? We follow a decision tree model, right? So what is a decision tree model? So every time we are comparing two elements, right? And once we find that, okay, a particular element is lesser than or smaller, then we are trying to compare that element with the element which is remaining. Okay, so basically in decision tree model, ultimately we make a full binary tree that represents the comparison between elements by a sorting algorithm. Okay, so internal nodes contain indices to be compared. So what is a decision tree model? Suppose I have a decision tree like this. So if I say 1:3, okay, so I am trying to say here that I am comparing between node 1 and node 3. Not node 1, node 3. You can say I am trying to compare index 1 element and index 3 element. Internal node contains indices to be compared. Right? And then what we do is we have an approach in our decision tree model. If index 1, the element at index 1 is less than or equal to index 3, we will follow the left branch of the tree. But if it is greater than, we will follow the right branch of the tree. Okay, so ultimately, if we keep on doing this, right, what happens? Every leaf that you find is going to represent a particular pattern. Okay, so what will that be? That will be a permutation of the input. So leaves contain a complete permutation of the input. Okay, for example, this is just for the example which we will see in the next slide. Okay, what we are trying to say, we are trying to say that, just forget this, this is just for one reference. So suppose this is, let us say, at end of, I have a small binary tree, and at the end for a leaf, this is the permutation. This is the at the end of the leaf, this is the you can say the structure that I get at the end of the leaf, that says 132. Okay, so 132, it says that this is index 1, index 2, and index 3. So it says 132. 132 means first I will represent 1, then I will represent 3, and then I will represent 2. So if you go at the end of this leaf, if it says 132, it says that this is the original array, let us say. So 132 is going to tell me 1, 3, and 2. So this way it is sorted, let us say. Okay, another example is, suppose this is given to me 7, 3, 12. This is the input is different, 7, 3, 12. And in a particular leaf, I get this kind of a structure, 2, 1, 3. How do I get this structure? While traveling the tree. If I get this, then my answer is going to be 2, 1, 3 means first 2, then 1, and then 3. This is just an example. But it is, so why this has come? We have picked up a leaf. We have picked up a leaf that has given me the sorted input. I have picked up another leaf that has given me the sorted input. Okay, so leaf will actually represent the complete permutation of the input. So not all the leaves are going to represent the sorted input. Right? We will see how it is. So tracing a path from root to leaf gives the correct reordering or permutation of the input for a given input. Okay, so we will see that how exactly it happens. We already know this. We have already done this. Probably this is a revision for you. Okay, so what we are doing in a decision tree model, we are saying that what we do. Okay, I will just tell you the structure and then we will trace it with one example. Okay, so we are saying here 1:2. Okay, so we will compare index 1 with index 2. If 1 is less than or equal to 2, we will follow the left hand side branch. And if it is 1 is greater than 2, we are following the right hand side branch. Okay, so for a particular example, let us say we have some example. And now if I find that 1 is less than 2, 1 is less than or equal to 2, let me call it as less than only now. Okay, so but it will work for less than or equal to also. So if I find 1 is less than 2, then what we do is we compare between, in this branch, we compare between 2 and 3. Okay, because we have already found that 1 is less than 2, so we compare between 2 and 3. Now if I find 2 is less than 3, So that means I have reached to a branch where I am saying 1 is less than 2, also 2 is less than 3. Right? 1 is less than 2 and 2 is less than 3 means what will be the sorting order? 1 and then 2 and then 3. Because I have reached here by saying that 1 is less than 2 and then 2 is less than 3. That means this is my sorted order. Right? Now, suppose I go here. I have already found out that 1 is less than 2, but 2 is greater than 3. If I come here means it is proved that 1 is less than 2, but 2 is greater than 3. So now I do not know what is the relation between 1 and 3. So we compare between 1 and 3. Right? Now we compare between 1 and 3, and if we find that 1 is less than or equal to 3. If 1 is less than 3, that means my sorting order is going to be 1, 3 and 2. Okay, so if my 1 is less than 3, my sorting order will be 1, 1, 3, 2. And if 1 is greater than 3, then my sorting order is going to be, because 1 is greater than 3, 3 will come first. And I already know 1 is less than 2, 1 will come here and then 2 is going to come here. Okay, so basically what is going to happen here ultimately, if I put any, this is a binary tree wherein this is a decision tree model wherein in my input there are only 3 elements. Right? Now I give any element. Okay, there will be different elements I can give. Sometimes 1 is greater, sometimes 3 is greater. So accordingly, I have to follow a different path. But at the end, in every leaf, that this is what is found now. This is what is very much prominent now, that based on the sort, based on, the order of the elements, how the elements are, we are going to follow to one of the leaf, and each leaf element is going to give me the sorted order based on what is the input. Right? So initially, I told you before we started this decision tree model, that all the trees will not give me the sorted order. Okay, all the leaves will not give me the sorted order. The meaning of that was based on the input. For a particular input, I will fall into a particular leaf. Okay, but for the same input, if I go to any other leaf, that will not give me a sorted order. Okay, but based on the input, we will fall into a particular leaf, and that leaf is going to give me the correct order. So in general, you can say that all the leaves are going to give you a correct order because they are giving all permutations of the leaves, all permutations. So depending on which input we have, we are going to follow one of the branch. Similarly, we go to the right hand side. So suppose 1 is greater than 2. That means I come here, then I want to compare if 1 is greater than 3 also. Yes, if 1 is also greater than 3, that means I have come here. 1 is greater than 2 and 1 is greater than 3. That means if you see here, both the branches, 1 has come at the end because 1 is greater than 2 and 1 is greater than 3. But we also need to compare between 2 and 3. Right? So now if 2 is less than 3, means 2 will come before 3. If 2 is greater than 3, then 2 will come after 3. Right? And now if we find that 1 is greater than 2 and 1 is less than 3, that means we will end it up here itself. 1 is greater than 2 and 1 is greater than 2 and 1 is greater than, 1 is greater than 2, but 1 is less than 3. So that means the sorted order ends here itself. Okay, so let us say, suppose we have this example. We have been given 12, 7 and 3. That's what was there in the previous slide. 12, 7 and 3, but we had 3, 7 and 12, but now we are taking a different input. 12, 7 and 3. So here 1 is 12, 2 is 7 and 3 is the index number 3. Now we have taken a worst case input, right? 12, 7 and 3. Why we have taken worst case input? Because we want to understand that how many maximum number of comparisons we will require. This is a worst case, 12, 7 and 3. Right? We want to sort them in increasing order and it is given in decreasing order. So let us say 12, 7 and 3, it starts from here. So first it compares 1 and 2. So 12 is greater than 7. So we will follow the right hand side branch. So we will have a comparison whether 12 is less than or equal to 7 or 12 is greater than 7. So we find 12 is greater than 7. So we follow this path. Now we need to compare 1 and 3, that is 12 and 3. Right? So now we compare 12 and 3 and we find that 12 is greater than 3. Right? So we are coming to this branch. So now we need to compare 2 and 3, right? So 2 and 3 means now we are comparing 7 and 3. Is 7 is greater than 3? Yes, 7 is greater than 3. That means we are going to come to this branch. And this branch tells us that the reordering should be like this. 3, 2 and 1, right? So 3, 2 and 1 means now this is what we have to do. 12, 7 and 3, it has to be 3, 2 and 1. That is what is my decision tree model. So 3, 2 and 1 tells me that this is the sorted array 3, 7 and 12. Okay. Now let us take another example 7, 12 and 3. In this case, first we are comparing 7 and 12. So 7 is less than equal to 12. We are coming here. Then we need to compare between 2 and 3. That is between 12 and 3. And we find that 2 is, we find here that 2 is greater than 3. So we come here. Then the next comparison we need to do is between 1 and 3. Between 7 and 1 and 3 means between 7 and 3. And we come to this branch. So this branch says that the order has to be 3, 1 and 2. 3, 1 and 2 means 3, 7 and 12. So what we did was we made a complete binary tree for 3 elements. Now you give any combination of any, you give any permutation, or you can say you give any 3 numbers, you will fall into one of a different, one of the different leaf, but whichever leaf you will fall, that is going to give you a sorted order, because all the leaves are giving you a permutation of all the elements based on whether, which, based on the comparison, right? So we took the worst case example, right? This was a worst case example. And you remember that in the worst case, how many comparisons we had to do? This was the worst case, right? How many comparisons we had to do? 1 comparison, 2 comparison, and 3 comparisons, right? So, and you know that what is the height of the tree? The height of the tree is 1, 2, and 3. If you consider this as 0, so 1, 2, and 3. 3 is the height of the tree. And how many comparisons we did? We did 3 comparisons, right? Because after doing the third comparison, we are reaching to one of the leaf node. Okay, so that is what is important. So how many leaves are there in a decision tree? Right? So the decision tree will be a complete binary tree, isn't it? You saw the decision tree because it has to be a complete binary tree. What is a complete binary tree? That a node will either have two children, or it will be a leaf node. That is your complete binary tree. So how many leaves are there in a complete binary tree? If you see this, 1, 2, 3, 4, 5, 6 leaves are there. Right? No, complete binary tree means all the nodes have, either they should be a leaf node, else all the nodes should have the, all the nodes should have 2 children, right? That is the complete binary tree. Correct, students? This is not, I will not call this as a complete binary tree. Why? This is a binary tree. This is a binary tree. Why this is a binary tree? Because each of the intermediate node also, if you see, it has either 2 children, or it has, it is a leaf node. It does not have a children because it's a leaf node. Okay, but if it has a children, then it has to have 2 children. So this is a binary tree. But what is a complete binary tree? Complete binary tree is a binary tree wherein each intermediate node has to have 2 children, or else it should be a leaf node. Here this is a leaf node, but but it's an intermediate node. It is not, this node does not have 2 children. Okay, so this is not a complete binary tree, because the complete binary tree is going to have, if the height of the tree is h, it is going to have 2 to the power of h children. Because every time, if for the root node you have 2 children, next time you will have 4 children, total 4 children, 1, 2, 3, 4. Next time there should be 8 children, 1, 2, 3, 4, 5, 6, 7, 8, right? So how many leaves are there in a decision tree? Right? So in decision tree, it is not necessary that it is going to have, it's not a complete binary tree, right? It's not a complete binary tree. Why? Because, we saw one example that once this is the condition, it is ending here itself. Once we found 1 is greater than 2 and 1 is greater than 3. 1 is greater than 2, 1 is greater than, and 1 is less than 3. So we know this is a sorting order. So a decision tree is not a complete binary tree, right? But what question we are asking? We are asking how many leaves are there in a decision tree. Okay, so leaf must have all possible permutations of the input. What is the definition of a leaf in a decision tree? A leaf must have all possible permutation of the input, right? So here, all the possible permutations, if you see 1 2 3 1 3 2 3 1 2 2 1 3 2 3 1 3 2 1, any other permutation is remaining? No, right? Why? How did we get it? We are getting 1 2 3 4 5 6, right? So can you tell me in terms of formula, right? For complete binary tree, it is 2 to the power of h, where h is the height. The number of leaves in a complete binary tree is 2 to the power of h, where h is the height. Now, can I put it in terms of a formula for decision tree? How many leaves will be there in a decision tree? The condition is given to me that all the leaves are going to represent one of the permutations, right? So let us see, did we cover all the permutations? 1 2 3, then 1 3 2, 1 3 2 is covered. And then let's start with 2 2 1 3, then 2 3 1. Let's start with 3 3 1 2 and 3 2 1. Yes, someone is telling. Someone, one of you is trying to say the answer. No, please say. So it is, the number of leaves in the decision tree is equal to the permutations that we are going to get with n number of nodes, with n number of elements. So what is the formula for permutation? Right? So here it was 3, right? And you got six permutations, no? All of them. So it is 3 into 2, isn't it? It's a simple permutation, is very simple. First I will place, I have been given 3 indexes, 3 places. So I can put in the first place, I can fill the first place by 3, right? Simple. The first place can be filled by 3 elements. And once I have filled the first place, now I am left with 2 places. And the condition is I cannot repeat the same index, right? So once I have filled the first node, the next place I can fill with only 2 places, right? And once I have filled with these 2 indexes, then the last place I can fill with only 1 index, right? So it is 3 into 2 into 1. What is that? 3 factorial of 3, right? It is factorial of 3. Very simple problem. We can solve it by doing this, because if I have 3 indexes and 1 index cannot be repeated. So the first place can be filled by n numbers. Next place can be filled by n minus 1 numbers, like that. So n into n minus 1 into n minus 2. So it is going to be factorial of n. Here my n is 3. Okay. So this is what. So what if a decision tree model did not? So we are asking a question that leaves must have all possible permutations of the input. We are saying that, is it, what if, what will happen if the decision tree model does not have all possible permutations? That won't happen, right? That won't happen, because in the comparison kind of sorting, where we are making a decision, we are considering each of the element, right? So that won't happen in decision tree model. If we are following a decision tree model, we are going to have all possible permutations of the input. That is what we saw. That's why we took a simple example with only 3 nodes. Okay, so it is going to have, understanding a decision tree model with more than 3 nodes is quite complex. With 4 node itself, it will be, how many combinations it will have? 4 into 3. 12 into 2, 24 combinations we are going to have. It will be factorial of 4, right? But it doesn't happen, it happens. Some input would exist that didn't have a correct reordering. So we are saying that in decision tree model, okay, so maybe there may be some input, they will be existing, but they will not have a correct reordering. But if we are so this is a case where, we are not exactly dealing with numbers probably. Okay, but in the example where we are dealing with numbers, that will not happen. Okay, so input of size n is going to have factorial of n leaves. That's what we saw. So basically we are going to cover all the combinations, right? So less than or equal to, we will follow the left hand side branch. Greater than, we are going to follow the right hand side branch. Okay, we can try that out, it will work. Okay, so now the question is, what is the worst case number of comparisons for a tree, right? That is going to give you a lower bound. What is, let us see, what is the worst case number of comparisons for the tree? How many comparisons we did? We saw that we did 3 comparisons. That was equal to the height of the tree, right? So this case we did. So the longest path in the tree, that is the height. So this is the path 1, 2, and now this is the third. If you call it as a path in the terms of a graph, this is one path, this is second path, and there will be third path, either this or this. Or in terms of comparison, if you say the 3 will come like this, 1, 2, and 3. That is equal to the height, right? So what is the maximum number of leaves a binary tree of height h can have? Now the question is, we saw that in a decision tree model, the number of leaves we are going to have is factorial of n, right? But we know that the maximum number of leaves a binary tree of height h is going to have 2 to the power of h leaves, right? So now this is what we are trying to understand. Okay, so in my decision tree model, I have leaves as factorial of n, and maximum leaf that I can have is 2 to the power of h, right? So this, I need not say, this is going to be 2 to the power h is greater than or equal to factorial of n. Now you have seen that, right? It's a simple example wherein you saw where when the value of n was 3, right? You saw that the number of combinations are going to be factorial of n, and you saw that if it was a complete binary tree, it is going to have more leaves. So we will say 2 to the power h is greater than or equal to factorial of n. We are trying to find a lower bound, basically omega. Okay, so what is going to be the complexity? The complexity is going to be minimum of this. Okay, so why we are not saying it to be your big O represents the upper bound, right? Which we say that the complexity is going to be less than or equal to this, right? But here, since we know 2 to the power of h is greater than or equal to factorial of n, so we are trying to find out the complexity, what it is going to be, the minimum complexity, what it is going to be. Okay, so 2 to the power h is greater than or equal to factorial of n. So if you take log at both sides, this is what you get. H is greater than or equal to log of factorial n, right? So then if that is the case, you can say that the height, h is equal to omega of n log n, right? So it is log of factorial n, right? So what is factorial n? Factorial n is nothing but n into n minus 1 into n minus 2, like that you can do the computation, right? So when you do it, it is inside log, you have something. Now if you try to see n into n minus 1 into n minus something, you can say it is n to the power of n, right? Log of all that n to the power, if suppose you open it. Okay, now if you ignore rest of the combinations and if you just consider n to the power of n, right? So log n to the power of n, if you compare, right? So then what you get is, you get it as n log n. If you ignore rest of the components here, right? I think it is clear, right? It is going to be n to the power of n, so that becomes n log n. So because your h is greater than equal to n log n, we are calling it, h is going to be, this is not the complexity, we are talking about the height. Okay, so h is going to be omega of n log n. Now why we are saying this is h, this is what we are getting, and we are saying that why this is we are talking about height, but we are representing it in form of the complexity. Why? Because we know that in case of a decision tree model, the maximum number of comparison, the longest path in the tree, okay, is going to be the height, right? The longest path in the tree is going to be the height. So what is my height, right? So my height is So the height that we are getting is, if you put it in these forms, so the height is greater than or equal to n log n. Okay, so what we are trying to say is, we are trying to say that if it is greater than or equal to n log n, so I can always say that, forget this omega. Okay, let me not call it omega or o if that is creating a confusion. What we are saying, you just see this formula. So complete binary tree has 2 to the power of h leaves, wherein you saw that 2 to the power h is greater than or equal to factorial of n, right? If h is the height. Okay, I'm not saying h can be n or nothing. I'm just saying that the complete binary tree has 2 to the power of h leaves. So 2 to the power h is greater than or equal to factorial of n. So you take log both sides. So h is greater than equal to log of factorial of n. Just forget this omega for some time. Okay, what we are saying is, and you say h is greater than equal to only. You say h is greater than equal to n log n. So if I replace n factorial as n into n minus 1, and I get a term with n, n to the power of n, and I ignore everything, I say that h is greater than or equal to n log n. So what it tells me that the minimum value of h is n log n, right? Minimum value of h is n log n. H can be more than n log n. Okay, h can be more than n log n. Right? So what we are trying to say here we write it h equal to omega n log n. What we are trying to answer is, we are trying to answer the question that we asked for comparison sorting, that can we do better than n log n? Right? That was a question, that can we do better than n log n? And we saw. So how we are trying to answer that question is, we are saying that, 1 minute students, these first year students, they see that I am in the meeting still. They are trying to call, and their exam was day before yesterday. I completed all vivas yesterday and day before. Still, they will have something that I can't tell you. It's really difficult for handling this first years, because they have not seen the college, right? They have not even come to campus. You people have at least attended the campus, right, for 2 years. So you know all the norms, everything, right? And the first year students feel that, teachers are always available for them. Okay, so even if yesterday I was having a class, I received so many calls, I had to cut it in between. It disturbs in between. All right. So what we are trying to say here is, 1 minute, I will cut this all. Okay. So we are saying that the value of h is going to be minimum n log n, right? And the value, and this h is nothing but, that this is the number of comparisons we need to do. We may have to do less comparisons also, right? This is the worst case. At the worst case, we have to do the number of comparisons as n, as the height of the tree, and that is going to be greater than or equal to n log n. So that is why we are saying that the question asked was, in comparison sorting, can we do better than n log n? No, we cannot do, because this is the minimum value. H has to be greater than or equal to n log n. Right? So this is the best value that we can do, n log n. We cannot do better than this in comparison based sorting. Right? So you can answer this question by saying this also, what is the height of the tree? Right? What if you have a tree with n nodes, you want to make, what will be the height? Okay, so your h is going to be greater than or equal to n log n. So that's the answer. Can we do better? That was a question asked. Okay. So if we are doing comparison based sorting, we found out that the maximum number of, in the worst case, the maximum number of comparisons that we need to do is equal to the height of the tree. And this is what we found out. For the height of the tree, it is n log n. Height of the tree comes as n log n. Is greater than or equal to n log n. So for comparison based sorting, we are not doing it more. We cannot find a bound which is better than n log n. Okay, so that means it is omega of n log n, because the complexity can be more than n log n. So n log n is not O basically, it is omega, you can say, right? We are not able to do better than n log n. right? We cannot reduce the complexity, means n log n, we can find the time taken or the time complexity which is more than n log n. Okay, so that's it, students. You already knew this. Yeah.
Ma'am, there the n factorial denotes the number of permutations, right?
Yes. Yes.
Uh, so the number of permutations is the maximum number of swappings or comparisons we are doing.
The number of permutation is this. Permutation is this. Okay. What is permutation? Permutation is like, okay, let me not go into that. Permutation is like this. You have three indexes, let us say 1, 2, 3. Okay. So what all permutations are possible? You can put 1 in the first place, then 2, 3. It can be 2, 3, and or then it can be 3, 2. Right? Then if you place 2 at the first place, then the permutations, basically this is not permutation, this is called as combination, right? You have 2 and then you can place it as 1, 3. Sorry, permutation will also tell you the place. So this is 2, you have 1, 3, or you can place it as 3, 1. Right? Now if you put at the first place 3, you have 2, 1, or you have 3, you have 1, 2. Right? So you understand it like this. You have indexes, right? So, and if you have 3 indexes, right? So you can place the first place with 3 in any of the 3 indexes. Once you have utilized one of the index, the next place you can fill with only 2 indexes. Once you have used the 2 indexes, the next place you can fill up only with one index. That's how you are getting it as factorial of n. Is it
So,
clear?
yes,
Yeah.
ma'am.
Yeah.
2 power h is the height of the tree.
Yes. No.
So,
2 power h is not the height of the tree.
I mean total
So
number of
this,
nodes in the tree. H is
no,
where h is.
no. Not total number of nodes. It is the number of leaves in a complete binary tree. Number of leaves in a complete binary tree. 2 power h is the number of leaves in a complete binary tree.
Yes, ma'am.
Okay.
Understood.
Yeah.
Yes.
Yeah. Right? So what we are trying to say is, if it was a complete binary tree, it will have 8 leaves, right? 2 more will be added here, 2 more will be added here. So number of leaves in a complete binary tree will be greater than or equal to number of leaves in the decision tree, right? Decision tree is not a complete binary tree, right? So that's what we are saying. So the number of leaves in a complete binary tree will be greater than or equal to the number of leaves in the number of leaves in the decision tree. Okay, yeah, fine. Thank you, students. So this was about the linear sorting. So you knew all this, but probably I thought we need a revision. Okay, if we ask such questions, but I was really happy that you spoke about counting sort and radix sort. Okay, so yeah, so we have to be specific. Okay, if we are talking about comparison based sorting, then we are saying that we cannot do better than n log n. Okay, so the name of the next topic is data structures. Okay, which you are well aware of. Okay, so I am not going to tell you about what is a stack, what is array, what is queue, and all those things, what is tree, nothing. Okay, but maybe something that you have, something that we will talk about. One we will call of dynamic sets. Okay, you also know about sets. Okay, so we will talk about sets, and I will quickly ask you questions. Maybe how much, what is the complexity when you delete an element from the array, what is the complexity when you pop out an element from the stack, or something when you delete an element from the queue or delete an element from the linked list. Okay, and something new we will talk about linked list. Okay, that linked list also you must be thinking what new. Okay, one new concept we will talk about list. So today, now it's already 9:30. So we will just get started with this. Okay. So to get started, I will be opening, this is the book. Okay. This is the book, that is Introduction to Algorithm by Corman. Okay. So we are where we are. Okay. So from where I have taken in the book, this is, you see that, the part one is foundation. Okay, so it tells about all this, the role of algorithm in computing, getting started, growth of function, divide and conquer, probabilistic analysis, and randomized algorithm. So from the book, we have covered few things. Then you have sorting and order statistics. So this all is considered. Uh, First is foundation, second is sorting in the book. Okay, it talks about heap sort, quick sort, sorting in linear time, median and order statistics. We did not cover all that. Okay, assuming that you have done, you already know it. Then the third part is data structures. Okay, the third part is data structures. So it talks about elementary data structure, and these kind of things are here. So I have taken from here. So this is third data structure, and I think this is chapter number 9. We are in page 30. Yeah, no, chapter number 9 is over. So this is this chapter 10. This must be chapter 10. Yeah. So this is overview of the data structures. Then how does he give is, he gives that, the author gives, something about the data structure, elements of dynamic set. Generally, students, or we don't read this, the preface of every chapter, we don't read it, but the important concepts are hidden there. Okay, and then operations on dynamic sets, overview of part 3. Then chapter 10 is about elementary data structures, wherein it talks about stacks, queues, everything is given here. How to find out stack, empty, all these algorithms. I am not going to discuss all these, students. I will just ask you, there are some exercise questions also. I will just ask you some questions from here. Okay, and whatever is new, that I am going to cover. Okay, so why I showed you this chapter is because I could not make very nice slides, students, because I have copied straight from the textbook. That's why I showed you that from where I have copied. Okay, so because the content was such that it was not possible. Yeah, I can copy paste line by line also. Not that I could not copy paste. I can always do that copy pasting from the book. It is possible, but the whole content was really important, that if it is called as reading out, I was supposed to read it out. So few things, few concepts, I have straight away copied the paragraph by paragraph for 2-3 slides. Okay, so that's why I showed you the book as well. And my idea is, I don't know how much time you find, and with this digital world, students don't have patience to read the book, but it is always nice to read book. Okay, so I don't want to comment on that, because I also understand you have the time crunch, lot of time crunch. Okay, so this is what is straight from the book. I felt I have to put everything from here. So basically it is telling about sets. So you must be thinking, what is great in that? We all know the sets. We know the concept of sets, maybe starting from our chapters, from our class 7th or 8th, when we studied about Venn diagram, right? From there itself we know the concept of set, union, Cartesian product, intersection, everything. Okay, so I'll still read it out. Okay, so sets are as fundamental to computer science as they are to mathematics. Actually, we cannot separate out mathematics from computer science. Without mathematics, we cannot do computer science. Okay, so whereas mathematical sets are unchanging, there is a difference, right? When we consider in maths, sets are unchanging. Okay, the sets manipulated by, but what is the difference between the sets we talk about computer science and the sets we study in mathematics? Okay, so the sets that we study in computer science, so the sets that we study in computer science, they are the sets manipulated by algorithm, they will be manipulated by our algorithm. They can grow, they can shrink, or they can even change over the time. Okay, so we, in our, while writing our algorithm, we assume a set, but the definition of set in your mathematics, there also there is a, when you say set is a number of finite elements. Okay, wherein you know that which are all element are going to come there. Okay, so in case of computer science, we call such sets as dynamic. Our definition of set will make sets to grow, they may shrink, You can remove the element from the set, and the set can change over the time. So we are going to call such sets as dynamic sets. Okay, so here so we are in chapter 10. Okay, so the author says that the next 5 chapters present some basic techniques for representing finite dynamic sets and manipulate them on a computer. So we are assuming that the sets are dynamic. Okay, that means they can change over time, but they are finite. They are not infinite sets, and they can be changed by the computers. Okay, so algorithms may require several different type of operations to be performed on sets. Okay, for example, many algorithms need only the ability to insert elements into, delete elements from, and test membership in a set. Right? So a set is given to me. I just want to do 3 kind of operations based on my algorithm is such that I want to insert an element, I want to delete an element from the set, or I want to test whether a particular element is a member of the set or not. Okay, we call a dynamic set that supports these operations a dictionary. Right? So it is also defined a new term that is called as a dictionary. What is a dictionary? It's a dynamic set. Dynamic set means it is not fixed. It can grow, it can shrink, or it can change over time. Okay, so a dynamic set which is able to perform these 3 operations. What are those 3 operations? Inserting an element, deleting an element, and testing a membership. Okay, this set is called as dictionary. Okay, but there can be other algorithms which may require more complicated operations. So in this course, whenever we will use the term dictionary, we will assume what is a dictionary. It's a dynamic set which can support these 3 operations. So we'll wind up here, students. We'll continue with this in tomorrow's class. So probably you can just revise the the complexity of various operations in stack, in array, in queue, because I will just ask you. Okay, I will not tell this is it. I will ask you, and if somebody has a doubt, you yourself will clarify that. Okay, so have a nice weekend, students. We will meet next Monday only, right? And it's going to be a festival time also, right? We have Onam on Saturday, and Friday we have Var Mahalakshmi, right? So have a nice festival, students. And there is a good news also. You must know, right, that Amrita has got a NAC A++ grade. Do you know that, students?
Yes, ma'am.
Yeah. So congratulations to all. So it all happened just before the festival time. So happy Onam, happy Var Mahalakshmi, students. So we will meet on Monday after the festival, right? So enjoy, students. So fine, we will wind it up now. Okay. Yeah, I'll wind it up.
Wish you the
So
same.
Thank you, ma'am.
thank you, students. Thank you. So have a nice celebration. Yeah.
Thank you, ma'am.
Thank you, students.